Good afternoon and welcome to today's webcast entitled Increase Combustion Turbine Output and Profitability, Overcome Temperature, Altitude, and Humidity Considerations. My name is John Evans with Webcast Experts, the producer of today's event. We are a division of Krishnan and Associates, a provider of technical marketing and business development consulting services specifically tailored to the global energy and power generation industries. Our presenter today is Mike Huft, Director of Commercial Operations for Powerphase International Limited. Powerphase delivers high-value products for optimizing gas turbine fleets for power producers worldwide. Mike Huft is based in Dubai and has over 17 years of experience in the power industry with commissioning, field services, operations, and general management in several positions globally. Prior to joining Powerphase, he was recently responsible for Alstom's generator service business unit in the Middle East Asia region, involving both Alstom and non-Alstom equipment. This included having responsibility for a large service workshop in Dubai. Mike holds an electrical engineering degree with a specialization in power generation and transmission. If you have questions as this presentation proceeds, simply write them into the Q&A box on your screen. We will address as many questions as time permits at the conclusion of the presentation and provide email responses to any questions that we can't get to. Without further delay, we'll now turn the presentation over to Mike Huft.
Thanks, John, and hearty welcome as well from my side to the audience. I'm today presenting the Turbophase dry air injection technology, providing an output and efficiency increase to combustion turbines at any OEM. And I would just like shortly go through the agenda of today. I would spend some time into who is Powerphase, what is the company history, then what is Turbophase and what are the benefits. I would then go to the components of the Turbophase module. Why is Turbophase efficient? I would go into the site interconnections and the controls and logics. I would then address a question in regards to real-time data that are focusing on compressor backsurge and stall limits. I would go into two typical GT frame real-time data and discuss that, and would then at the end give a short overview of the maintenance cost of the Turbophase module. And once this is done, we are then having time to discuss questions which I will answer then and address then. So, who is Powerphase? Powerphase is a US-based company headquartered in Jupiter in Florida and having offices in Middle East and in Asia. I'm heading the Dubai office here, in charge for the Middle East, African, and Central Asian market. Powerphase has been founded with the aim of addressing nowadays challenges in power generation, focusing on efficiency and sustainability. And the company has been founded back in 2012 by a gentleman called Bob Kraft. Bob is actually a well-known fellow in the industrial world. Bob's first company was called Power System Manufacturing, PSM, in which he has designed advanced gas turbine parts and components. The company then has been acquired by one of the large OEMs, and Bob has left the company back in 2010 then to focus on this Powerphase company. So we are all engineers of different capabilities from OEMs, and so we have a broad and comprehensive knowledge and understanding of what we are doing. So we know what a combustion turbines, how a combustion turbine functions. That is a short introduction. We go now into the section of what Turbophase actually is and what the main benefits are provided to the end user. A simple introduction is that the Turbophase module is an external turbocharger that is connected to the to the compressor discharge section of any gas turbine, injecting dry air into this plenum. With that, depending on the size and on the frame of the gas turbine, we are introducing 10 to 30% power increase. We are able to increase the fuel efficiency by 3 to 8%. We are competitive in pricing compared to upgrades on new installations. And we provide a great flexibility just with focus on the new renewables like wind or solar. The key benefits in more detail are the output increase, as just mentioned. So we actually, as a ballpark, bring the output back to the ISO condition of the gas turbine, independent on humidity, temperature, or elevation. We are a fast response. We can inject dry air within 60 seconds from the demand signal. That means we are actually a fast response, and in some markets we are representing spinning reserve. We are environmentally friendly. There is no water consumption in our system, not for the operation of our system, neither for the augmentation or the enhancement on the gas turbine. We have an impact on a positive impact on the efficiency of the gas turbine. As we just inject dry air, there is no maintenance penalty on the main equipment. And combining all of these benefits, we are actually talking about a fast return of investment. On the capacity and energy section, we increase reserve margin and all the auxiliary power required on certain power stations. This is actually showing two of the Turbophase modules. It is a 40-feet container that is modular, and it's scalable to the size of each gas turbine. The module itself is always on the same dimensions based on the gas turbine size. It is just scalable up to 8 modules, for example. That is simply caused by the fact that bigger gas turbines have a higher mass flow, and we want to account with our dry air injection, we want to account for maximum of 5% of the main mass flow produced by the gas turbine compressor. On this particular picture, you see 2 modules connected to a 6B facility, adding power or connected to 3 different GTs, adding power to either of them. I will come to that particular plant later on. The next picture is showing, the next graphic is showing the real footprint. It's a graphic showing an F-class 2 gas turbine power station, and you see on the right lower side, you see 8 Turbophase modules in the real time, or let's say in real scales, accounting in that particular power station setup for 52 megawatts. And you see the size of this Turbophase module place or Turbophase system containing out of 8 Turbophase modules is small compared to the overall size. And A big advantage here as well is that these Turbophase modules can be placed up to 1 kilometer away from the gas turbine in whatever situation, in whatever position. They don't have to be right next to the gas turbine. In the next slide, I'm actually addressing what we do. You see here two typical temperature versus power pattern over a day. On the left side, you see a typical 9E power output, and on the right side, it's a 6B power output. And what is shown here is that when the temperature is the highest, the output is the lowest, and that is simply caused by the density of the air at high temperatures, causing a reduced mass flow. And with a reduced mass flow, the gas turbine is unable to produce the required power. What we're doing is actually we are compensating for the missing mass flow. We are compensating the missing capacity due to high ambient temperatures or high altitude. And in the next graphic, we see actually what I just said. What I just said, we see here in a graphic. So the temperature range on the lower scale, and then the percent of the output on the left scale. And what we see is actually that at around 16 centigrades, each gas turbine has its design capacity, its ISO condition capacity. And if we go higher with this temperature, the mass flow and hence the exhaust flow reduces. With it, the output reduces. And by doing that, the heat rate, the efficiency actually reduces, the heat rate increases. And what Turbophase does is, depending on the design capacity of the gas turbine, we are adding our 5% incremental air to the compressor discharge, and adding and following actually the output of the gas turbine in parallel. And what is seen here, and that is supported by real-time data later as well, the performance, the added power on top of the gas turbine power is independent on humidity, temperature, altitude. So now we go, how does Turbophase work and what are the main components of the system? So we see 4 pictures here. We will start with the left upper one, where we see the sound enclosed, weatherproofed 40-foot container with its rooftop components, which is in this case here the recuperator or heat exchanger. I'm moving right now to the right upper picture, in which we see that the exhaust gases of the engine, of the reciprocating engine, are heating up the compressed air in the recuperator. Then I go to the lower left picture, in which we see that the compressed, heated and dry air are injected into the compressor discharge plenum, bypassing the compressor actually. And on the right lower picture, you see a benefit that it is a scalable modular system. In this very case, there are 6 Turbophase modules connected via a common header to 2 gas turbines, allowing maximum flexibility in terms of operation, in terms of maintenance, and so on. We go now to the general schematic of the system. On the lower portion of this screen, you see a combined cycle tail with the left side of it with the gas turbine and the gas turbine generator. And on the right side, you see the heat recovery steam generator, steam turbine, and the steam generator, the electrical generator of the steam turbine. And then you see on the upper portion of this picture, you see the blue framed box, which is reflecting our our Turbophase module, you see a reciprocating engine, which is either liquid fuel or gas fired, that drives an intercooled multi-stage compressor. I come to that point later on. And with the exhaust gases, we are heating the recuperator, the rooftop component. And once the air is matching the exact parameters of the given gas turbine compressor discharge in terms of temperature and pressure, then we are going to inject the air into the wrapper prior to the combustor. With that, we increase directly the output on the gas turbine compressor. And as we have increased the mass flow into the combustion of the gas turbine, the exhaust gas flow will increase as well, giving benefits on the steam cycle. For example, with the increased mass flow, duct burning can be compensated for. It can be switched off, and which has another benefit then in terms of fuel savings. With our injection, we are always looking into being below the design capacity of all components and injecting below ISO condition. In case we are going above ISO condition, a comprehensive investigation on site will be done in order to see about the capacity of the steam generator, of the steam turbine generator, and all electrical and mechanical components. So now I want to explain the components itself. So what we have here is, in our box, we are using standard components. There's nothing specially produced or manufactured for this particular module. So we use an MTU or cut reciprocating engine. As I mentioned before, we are burning liquid fuel, natural gas. We are dual fuel capable. Then we use a multiple staged intercooled compressor. Everything is done into the. Everything is compressed into the or comprised into the 40 feet container, and that is a complete factory assembled and tested skid that we just move, completely commissioned and tested to site, and reduce therefore the commissioning time and the installation time to an absolute minimum. A more detailed view on the components. I'm starting on the lower right side. So we have a cooling water inlet for the intercooled multi-stage compressor. We are either using plant water or we bring our own air-cooled air cooler with us. It's depending on the capacity of the plant and so on. We have heat exchangers in the module. We have our engine. We have a gearbox, and then we have the compressor. The compressor, of course, is intercooled, as mentioned. Then we have the inlet for the compressor, and depending on the environment where the box is situated and is operated, we are providing second stage filter, impulse filters with this box in order to ensure that the air we are injecting into the gas turbine is at least of the same quality in terms of particles, in terms of humidity, and so on. Then we go to the rooftop components. I start there on the right side. We have a small, we call it baby compressor, a small instrument air compressor for valves around our box. We have the engine exhaust going into the recuperator. Then we have the compressor outlet going into the recuperator secondary side. And then we have from the recuperator the air line going either directly to the gas turbine or going to via a common header with several of these boxes into a larger sized common header, and then distributed into a bunch of gas turbines. And then we have the silencer and muffler. Both are there in order to, in case that we have to interrupt injection, we want to discharge the air away from the gas turbine. So we have a control valve upstream of the compressor discharge casing. And what we are doing is, in case of any parameter of the gas turbine is indicating that we are not in normal or standard operations, then we are going to save and we are going to shut the control valve and stop our Turbophase module, and the air that is already in the piping will be discharged to atmosphere via the silencers and mufflers. So therefore we have these components. I want to emphasize once more that all of these components are standard. All OEMs of these components, especially the compressor and the engine, have a very well-established service network around the globe, and hence spare part availability and so on is well covered globally. I have mentioned the requirement of having having water into our box for cooling reasons of the intercooled multi-stage compressor. There are several options. One of them is that we use plant water. The plant water used or required is in the amount of 200 cubic meter per hour per TPM. We will return that in the exact same amount. We don't consume any. And the requirement of this cooling water is around 35 to 40 centigrades, and we will return it with 15 centigrades higher than we get it. In case the power station is not able to provide such amount of cooling water, we are going then to bring our own air cooler, our own fin-fan cooler, which is a closed loop cooling system, which then allows us to operate independently from the plant without any water requirement except or other than the initial fill of the system. And important here is that the option of these air coolers are not increasing the footprint significantly. So we are still at a very low footprint compared to the megawatt or kilowatt installed. The ratio is still very competitive and very low. I have mentioned before that the system is modular and factory acceptance tested. So you see on this picture here, you see a screenshot of the test stand of our supplier, or of our packager actually. The units are packaged in Korea. And you see here the test stand. And what we do is here actually we certify several parameters that are guaranteed or that we guarantee commercially to the end customers. It will be the airflow generated, it will be the air temperature and the air pressure, which are the main components or which are the permissive signals for the compressor discharge. So then we will have monitored the fuel consumption to see the efficiency or to monitor the efficiency. We will have a sound and vibration level acceptance. And we will of course have the auxiliary load and the safety functions, which are adapted to the site requirements. All of these tests will be witnessed by customer representatives, which are then going to the factory and see all the operations in the test stand. Once it is then ready and factory acceptance certified, it will be dispatched to the site. And at site it is just left, or it's just put into the foundations, into this place it has to be, and it is connecting to the pipes that we have already installed in the lead time of these modules. and that means that the real commissioning time of that Turbophase module is less than a week from arrival to site. That is possible because of that the installation, the airflow, the pipes and all components, the interfaces on site that I have mentioned before, will be done already in advance of or prior the arrival of this Turbophase module. And for example, the only thing that requires a shutdown of your plant is the tie-in to the compressor discharge casing, in which we normally use existing flanges or manifolds. On certain types of gas turbines, we use the rotor air-cooled manifold as well. And once this is the only place where we need, or the only time where we need a shutdown of the GT, and that is normally a 1 to 2 days shutdown that we require. So that's about how it works. Going back to the agenda, the next point was, why is it efficient? And why is it providing fuel savings? So what is this module? The module has a compressor, a multi-staged intercooled compressor, highly efficient. It has an engine, a reciprocating engine that produces actually heat, and we use this waste heat to heat up the compressed air to the required parameters with a heat exchanger. So what we actually see here is it is a small combined cycle where we use the waste heat, and with that we are compressing the air about 30% more efficient than the gas turbine compressor does it. How is it possible? I will just shortly go into the TS diagram here. What we see here is the blue. There is a blue line with 2 points, 1 and 2, which is actually showing the gas turbine work required for compressing the air via an actual gas turbine compressor. So this is actually on the left side. You see the small, you see the indication that the work required to produce the compress the air that is used for the combustion is taking approximately 50% of the turbine work. Now we look into the multi-staged intercooled option, which is the green line, in which you can see here that with 3 intercooling, this is a four-stage intercooled compressor with 3 intercooling cycles. The outlet of the compressor is point number 8. As we intercool it, we use, of course, less work to do that. We make it much more efficient, and to bring the compressed air up to the required temperature, we use the waste heat of the reciprocating engine, and therefore we make it actually, we are about 30 to 35% more efficient than the gas turbine compressor. And that results in the following short graphic. You see here a picture of an F-class gas turbine. You see our module graphically injects 5% air into the combustion, prior to combustion, into the compressor discharge casing. And on the graph on the upper side, what you see here is on the table on the upper side, you see that this particular gas turbine has a base power, or let's say has a base load of 300 megawatt. 150 of this power is used to turn the compressor to produce the air for the combustion, and hence the generator output of this particular gas turbine is around 150 megawatt. Now, with our Turbophase module, we inject 5% air. That results in a 17 megawatt output increase. As we don't have any impact on the compressor side of the gas turbine, as we inject it in parallel, the the output remains 17 megawatt. So if you look then at the weighted average, out of 5% in mass flow, we make actually 11% more output. And that is the reason we are more efficient, as simply for the fact that the compressor is using less power to compress the air. So this is why we are more efficient. Now I'm going to what are the site interfaces, what are the interconnections, controls, and logics. We start with a typical mechanical block diagram. To show the scalability here, I have used 2 TPMs. The blue box is in the center of the picture. And so this is the delivery scope. We have then a fuel gas regulator. So we bring as an option to our, or let's say as a standard delivery to our box, we take the plant fuel supply, that is one mechanical interconnection that we need. We take the plant fuel supply in whatever parameters delivered. We reduce it to the required parameters to operate both our boxes. So, and then we are with our fuel gas regulating skid. The other mechanical interface that we have is, as already discussed, the plant water for cooling reasons. So in this case, we say we receive plant water, we run it through both the TPMs with a pump, and returning it back to the plant in the exact same amount. For both of these TPMs, we would use 400 cubic meters per hour. And the third mechanical interface is the lower portion. It is the the air line into the gas turbines. And what we have here is the connection on a common header. We have air control valves in front of both gas turbines in this case, and we are injecting the air in existing manifolds, flanges, or rotor cooling manifolds. So these 3 things will be installed prior to the arrival of the TPMs, as mentioned, and the tie-in to water, gas, and gas turbine is normally not taking more than 1 to 2 days shutdown for this upgrade of the GT. The next picture will show us the site block diagram for the electrical and control. So here we have the interface of the electrical power. We would need from the plant 1 power feed to, as our standard TPM actually has a parasitic load of close to 30 kilowatt, which is very low. So we would require a 3-phase 380 to 415 50-60 cycles power supply. We would bring our own logic. So we will bring our own logic in the center of the point. You see the TPM master controller. We will bring our own motor control cabinet and the local HMI. Important to know here is that we don't interfere with the existing GT controller. So what we do is only we read data out of the gas turbine controller, and with this data read out, we are using for controlling our system and making the operation safe. We have several levels of integration. We can integrate it into the master, into your control room. We can integrate it in the DCS. We can make an automatic ramp up. We can have that even grid control, the TPM and the air injection. So we are flexible and follow here the requirement of the power station. Actually, once more important is we don't interfere in the existing GT control logic. Here, what we see here is actually just some screenshots from some existing existing operations. So we get the megawatt signal from the plant control center. It is either manually or automatic. I mentioned that. Gas turbine controls are unaffected. We read out permissive signals from your gas turbine controller or from your plant controls. For example, if the pressure in the compressor discharge casing is going to be low for whatever reason, or if the temperature is not matching, or if your gas turbine trips, then we are automatically shutting the valve and interfering or interjecting immediately into the so we're interjecting the air immediately, that there's no dry air injected into the existing operations of the gas turbine and harming the compressor. Many questions are, for example, what happens if the Turbophase module trips? What I have here, for example, is a typical operational pattern. You see on the right side the exhaust gas temperature. On the left side you see the gas turbine power. And what actually happens is, the gas turbine power, the blue line you see, is around at 33.5 megawatt, which is the equivalent on the 6B. And what happened actually is that we tripped on purpose the Turbophase module. What happened is that the airflow was reduced immediately, so the gas turbine went back to baseload. In this very instant, the exhaust gas temperature increased because of the missing mass flow. The fuel air ratio went into a richer position, and with the trip and with the missing mass flow, the exhaust gas temperature automatically goes back to where it was over a shorter time frame. So that is all done automatically by the GT controller, and our injected air is not going to interfere in that particular operation mode. So the next point on the agenda is questions that we normally receive on compressor back pressure or surge limits, and I would like to address this as follows. So there are there are some OEM positions, let's say. OEMs state in general that, for example, a 5% injection into the compressor discharge is allowed, that the gas turbines are concepted for it, are designed for it. Other OEMs, for example, endorse the dry air injection technology, especially for, or let's say for a particular frame in a particular area. So these OEM positions are available, they are published. And I would like to, in the following, I would like to go into some real-time data on the compressor surge margin. This is on a 6B. You see on the lower side of the graph, you see three orange squared points, which are actually which is the compressor discharge pressure without air injection. It is about 15% off the surge limit, which is the blue line at top, the surge alarm. Then you see 2 or 3 triangled gray points on the right upper side. These are the compressor discharge points, or the compressor discharge pressures, parameters with 1 TPM injection, so which is actually a 5% injection. And then you see on the left upper corner, there's one particular point in which we have injected 10% into 1.6B, and you see we are still about 9%, 10% off the surge limits. So we read all of these out, and we make sure that we don't pass the OEM recommendations on these particular frames. On another one, this is another real-time data. I will come to this particular installations in a bit. We see here as well there is an air injection and a no air injection, and with both of 2 TPMs we are 10+% away from the surge limit, which is actually here the more orange line, which is the upper orange line. So this is about to address how safe we are in terms of surge limits. I would like to go into 2 installations right now, on a 6B and on a 7FA. What we have here is a 6B installation in Morris. You see on the left side of this picture, in the framed circle, you see the 2 TPMs that I have shown you at the beginning of this presentation, right next to the chiller building. These 2 TPMs are connected on a common header, utilizing existing piping racks into the 3 6B gas turbines here in the middle, and allowing the customer a maximum flexibility in operational cycles and into plant maintenance. What we see here is, what I want to show with this graph is, in Morris, these TPMs are grid controlled. So whenever the grid requires more power, and that is at part load or base load, they are able to start them via the grid mode. You see here on the orange side, you see the base load of the gas turbine, which is 31 megawatt, and then you see 3 cycles here. These are real-time performance test data, in which you see the first 3 cycles are the injection from 1 Turbophase module, and then you see on the right side the last peak. This is the 2 TPMs injected into 1 gas turbine, and then we initiated a trip on the right side, and the gas turbine went back to base load. So as I said, real-time data. In the next slide, I want to show you an installation in the Middle East, which was a fast-track installation to cover summer peak. So we have the 2 Turbophase modules. We have a pulse air pre-filter as there were desert conditions. We have our cooling, our self-sufficient cooling system here, and then we see a long gas line into the gas turbine compressor discharge manifolds, and we were around 250 meters away from where the air is actually injected in the gas turbine. That project was a fast installation. It was done within 90 days, and it was done in time. From this particular project, I want to share some data with you. This is the output data. The blue line, the blue lower line, is the baseline of the gas turbine, which you see decreases over the temperature by almost to 20%. 20 megawatt, and then you see the red line, which is the injection of the first Turbophase module, and the green line is the injection of the second Turbophase module. So in total we added 9 megawatt, and these 9 megawatt were added over the entire temperature range. I have the same graph, not for the output, but for the efficiency, for the heat rate. And what we see here is that the base heat rate is the blue line, which is increasing over the temperature. Then we have injected with the first TPM, similar to the other picture, it is a red line, and the second TPM is the green line. And with the injection of 4.5 megawatt per TPM, we have decreased the heat rate by 0.85%. On this particular gas turbine, we could have installed 6 TPMs, making, or let's say decreasing, the heat rate, or accounting for direct fuel savings to 5.4%. And I have here, of the same gas turbine, a similar picture. So we have the base load of the gas turbine, 122 megawatt. And so we can, from the moment we switch the Turbophase module on, you see the immediate impact, which makes it really easy for performance tests and very straightforward in terms of what megawatt are we adding and what megawatt are we, or let's say what efficiency are we adding. And by that, it is important to mention that these kind of output and efficiency are guaranteed values that we commercially fix with any end customer. This is about real-time data. I would just now go into the TPM maintenance. I looked here, I took this graph here. The basis is a 4,000 operation hours per year. And you see on the lower scale, you see the, on the lower axle, you see the years. And at 4,000 hours, the first 5 years actually, the maintenance cost would account for $100,000 US. The engine will have a minor after 24,000 hours. We'll have the second minor after 48,000 hours, and we'll have then the major at around 62,000 hours, 64,000 hours. The compressor will have its inspection and maintenance at around 48,000 hours, and we are here flexible in hiding, I would say, hiding behind the plant maintenance, so there's no shutdown other than you already planned for your gas turbines, actually. And then the last slide I would like to present here is actually the Turbophase performance in combined cycle at several major frames on the 50 cycle and on the 60 cycle performance. So you can pick whatever gas turbine in open cycle in combined cycle, for example, on a 9E, we would add 16.9 megawatt with 3 of our Turbophase modules. So that is actually showing the performance of our modules and the flexibility of our modules. And with having said this, I would like to give it back to John and and open the question section.
Thank you, Mike. Very good. We do have some questions that came in during the course of the presentation, and we'll just step through them at this time. One question has to do with the cooling water. Is the pump provided by Powerphase, or is that something out of the battery limits that the customer has to provide?
No. So the pump is provided by Powerphase. And whatever I mentioned in terms of auxiliaries adapted in this system, we already account for in our heat rate and in our efficiency. So what I want to say is, if we for example say we need a water pump to transfer the water from the plant into our systems, then we would account for that water pump already in our net efficiency. So we power it. We power it.
Yeah. Okay. What is it's a 3-phase motor on the pump? So what is the power requirement typically?
It depends.
For the pump.
So yeah, it depends. It depends on the header of the water and on the place where we can tie off the water from the customer. If it is let's say a small distance, the pump can be smaller. If it is a longer distance, the pump has to be bigger. Typically, for a header of, let's say, typically for the 200 cubic meter, the pump size is, I would say, around 35 to 40 kilowatt.
Okay, very good. Question regarding the economy of the Turbophase. Is it more economical and efficient in terms of output compared to inlet air cooling of inlet air? How does it compare with that?
So the comparison with inlet conditioning as such, there are 3 major points to be considered. I have mentioned when we bypass the compressor. We bypass the turbine compressor, which means the inefficiency of the turbine compressor is not affecting the performance of our system. The performance, or let's say the air injected into the compressor discharge. Whereas if you do that on the inlet conditioning, reducing the inlet temperature actually by several means, you still have to pass through the compressor, which makes it less efficient, directly less efficient. The other thing is that the parasitic load for a chilling mechanism into the inlet conditioning is higher than it's normally higher, typically higher than for our system. And the third major point is actually that we don't have any. It depends on how do you look into inlet conditioning. For example, if you take an evaporative means, there are maintenance penalties associated to it, and of course the water supply, the water consumption, which is a big point. And so these three measures actually making our technology much more efficient, not only in operating, but as well in not only in the investment and in the efficiency of the turbine, but as well as in the operational costs such as water, Daemon water delivery, and so on.
Okay, very good. We assume that the calculation of efficiency accounts for the fuel for the resit drive on the compressor.
That's absolutely right. If we talk about efficiency and the efficiency that I have shown here into on several real-time data, that accounts for not only the fuel that we consume in our reciprocating engine, but as well for the fuel that the gas turbine uses for the excess air. So we add more air into the gas turbine, so the gas turbine burns for this incremental air more fuel. Both fuels in our recip engine and into the gas turbine, both are accounted for in our heat rate and guaranteed towards the customer.
Okay. You mentioned the bypass mode or the safe mode that you go into if you're taking the unit offline. And the noise level, you now go through a silencer or a muffler. And what is the noise level in decibels that you achieve when you have to go that way?
So our Turbophase module is sound enclosed, and we are actually going to be below into the below the, I think it was 80 decibel standards, a meter away from the enclosure. So this is international standard, and we can account for that in terms of yes, on the sound and on the sound level of these engines.
Okay, on slide number 17, while we're on the subject of the muffler, slide 17 shows the outlet of the muffler and the outlet of the silencer. Are those in series, or at times you go through the muffler and at times you go through the silencer, and what determines that? Slide number 17.
So both are different. We have, for example, in the ramping up time of our unit, we will have to discharge the air to some place until we are reaching compressor discharge casing conditions. So for that reason, we are discharging it until we reach it. So while ramping up, we are discharging it through the muffler. And whereas the silencer, the silencer just has a different noise level reduction, whereas the silencer is there to, if we have discharged the full amount of air already in the amount or already blown into the gas turbine, if this full amount, 6 kg per second of air have to be discharged, then we use the silencer. So these are the both different ways of discharging air. One is for the ramp up, the other one is for the full load stop.
Yes, I see. Okay. Question on the flue gas emissions. How does Turbophase influence the flue gas emission from the stack? Are there any implications on emission compliance?
So what we said is, or what I mentioned before, is that we are going into being below design criteria of the gas turbine. So having said this, unless we are below design criteria, we don't add any excessive exhaust into the stack other than the gas turbine would do as well at cold conditions. We have, though, and there's an additional fuel source to be evaluated, which is our natural gas engine. So if we have different options, we can use the exhaust of our gas engine to add it into the existing stack. But as well, we can treat the exhaust of our engines into the, let's say, to reach the most stringent requirements as well. So on the gas turbine itself, on the stack of the gas turbine itself by the operation, there's no impact other than when it was in a cold day, and adding the reciprocating engine, there we would account for, or let's say there we would treat the exhaust to the absolute minimum as required by the environmental figures.
By the permit, okay. When you have the higher mass flow into the combustor, does that imply a higher fuel flow, combustion turbine base fuel? And what's the effective heat rate of added fuel to the turbine due to the higher mass flow of the air?
So what we actually do is, if you can consider that the turbine burns the same amount of fuel, so that the combustion of the turbine burns the same amount of fuel for the air brought into the combustion, irrespective of from where it comes. Comes it from the external compressor, or comes it from the actual compressor of the gas turbine? The only point is that the air compressed by us, by the Turbophase module, is compressed with much higher efficiency. So at the end, if you look at the net efficiency of the gas turbine itself with our system and without our system at the same output, there is a significant heat rate reduction in due to the fact that the air we produce is much more efficient.
Okay, excellent. Have a question on a commercial question. Do you have any arrangements such as leasing the Turbophase module or any other arrangements for acquiring the equipment?
So we are actually flexible, and that is a part of the nature of our system, as it is an external system. There's no modification required. There's no internal parts required. So what we will do is we offer it as a normal purchase, a CapEx purchase. We are open to lease it over a certain time frame. We are open to enter an PPA, a power purchase agreement of whatever kind. We are able to look into BOOT schemes, for example. So we are indeed very flexible with this system to follow requirements of the customer.
Okay, excellent. Is there an expected ramp rate, load ramp rate in rate per minute? Is there a rate that you can cite?
The rate of the ramping of the gas of the additional power is similar to the ramp that the gas turbine it is connected to. So we are making sure that that these parameters are aligned, obviously with connecting it to different frames. We are then adapting the ramp rate to the existing gas turbine.
Okay. In a combined cycle, the additional air injected, how does that affect the pressure in the Herzog or the chimney? the downstream pressure? What is the effect of the injected air combined cycle?
As we increase the mass flow into the combustion, the exhaust gas flow will be increased as well. We are looking into that if we are above ISO condition, above design condition, or if we are below. If we are compensating for missing air due to high temperatures, the impact on the design criteria of the pressure of the HRSG on the stack there's no impact on above the design limits. The question is if the customer, for example, looks into an add-on of power above design criteria. In this very regards, we have to look downstream of the mechanical and electrical components, and that will be normally done by site visit and then excessive studies. But normally there's, so let's say, again to summarize, in below design criteria, there's no impact that is of harm.
And in that same token, you mentioned early on about no effects of SCR or CO catalyst. So there's really no special considerations around the pollution control with the added air, correct?
Unless we compensate for, let's say, in case we compensate for the missed air and operate below the design values of the gas turbine, you're absolutely right. There's no add-on in the pollutions or whatsoever.
Okay. For the OEMs for the combustion turbine, are there any special modifications in the chamber that are required from the OEM if a Turbophase is going to be installed?
No, it's not. Just to make it clear, let's assume there is a gas turbine operating at 40 C right now, or 35 centigrades, and then all in a sudden there's a temperature drop by rainfall or because a cloud is covering the sun. In that regards, there's an effect that the gas turbine is immediately ramping up power because the mass flow is simply higher than it was at high temperature. So we do the same. We are just independent on the rain or on the temperature, on the ambient temperature drop. So what we just do is we just inject air in addition to what comes from the compressor, and hence there is absolutely no modification required, not in the GT control, nor in the combustor, nor on the gas turbine.
Okay. If you're operating at base load and you have the Turbophase adding incremental air, what happens when you go to part load? Does the Turbophase automatically compensate in a partial load?
Yes. So it depends on the gas turbine operation mode. For example, if you are on firing temperature mode or in exhaust gas temperature mode. Generally, the behavior of the Turbophase module is the same. We get a demand signal of a megawatt demand signal if the customer wants to have, for example, less megawatt into our system or from our system. We are just following that demand signal. So if the gas turbine is ramping down to part load, we are considering this as well, and that's a case-to-case situation and implementation into the plant control on how the customer wants to have that implemented. But yes, we are following the demand control of the gas turbine or of the plant.
Okay. Another question on the installation interface. Do you provide vibration eliminators or specify what the customer has to require for vibration isolators or eliminators?
Yes, of course. So we are installing our system and operating our system based on the specific requirements on where we install it. If, for example, the customer or the authority is requiring a special vibration measurement, seismic measurements, or whatsoever, we can add this into. We either can add this into our option, into our scope, or we tell the customer, we define clearly what is required and so on. So we give a clear specification out on how to operate safe under the circumstance of environmental challenges and the particular gas turbine that we are connecting to.
Oh, very good. We have reached our time limit now, so we're going to have to conclude. I'd like to thank Mike Hook for this presentation today. We did have an excellent turnout, and I'd like to thank all of you attendees for spending some of their time with us this afternoon. This presentation has been produced and marketed by Webcast Experts, a division of Christian and Associates. And please keep an eye out for future events from us, bringing you more information on advanced products and services within the power generation industry. You may contact us at 1-203-921-1800 or email my colleague Luke Rathel, that's Luke, at webcastexperts.com for any questions you may have on organizing a webinar or any subjects of interest you may have for future webinars, or accessing any of our previously held webinars that are now available on demand. This concludes us for today. Thank you and have a good day.